The selective amplifier has been running as an oscillator for over 30 hours now. You can see from the spectrum here, the white trace is the average of 558 power spectra, while the green trace, which is much wider, is the collected average correlation spectrum over 30 hours. The signal has drifted up and down by about 1.5 Hertz, so it looks much wider in the correlation spectrum, and this makes the measurement of noise levels here in the region where the slope is large. It is some kind of average of the noise over a frequency separation span of plus minus 1.5 Hertz from the frequency that I measure. So this adds some uncertainty at close range. At wide range, the correlation spectrum looks very noisy. I don't know why, because the distance between the measured distance between the correlation and the power spectrum is 19.3. That's what I'm usually calling the correlation advantage, while the theoretical limit is 23.8. So that is almost 4.5 dB. Usually I want 6 dB, but that would take many more hours. So this spectrum with the delta 44 sampling at 8 kHz is useful only for a fairly narrow frequency range from maybe here to here or so. And the reason why the noise floor is flat here is unknown to me, at least right now. I will save this image and evaluate it with the pixel editor. And I have another spectrum running that's here. This is the UADC4 running at 44,100 Hertz. So it has collected many more average spectrum, and the theoretical limit is 27 dB. And it seems to work up to something like here before the data points become too scattered. It's difficult to see here because of all the spurs. There is every 50th Hertz from the audio. This is DC, and then there is 50 Hertz, 150, 250, all the odd overtones. And then there are modulation sidebands, 50 Hertz on each side of the strong signal. And then there are modulation sidebands on the overtones produced by the nonlinearities of the mixers. And those give some structure to the correlation spectrum. Anyway, I will save this information. Also, I read out the level of this point, the average power spectrum, and I will do things with the pixel editor. I have expanded the spectrum to save another image of the same collection of data, and I will evaluate also here the y-axis minus 158.5 and 17.9. That is minus 176.4. That's here, half a dB below, no, 1 dB below what I was seeing with the unit operating as an amplifier, amplifying the Wenzel oscillator. The Wenzel oscillator itself is here maybe 10 decibels, well, pretty accurately 10 decibels higher. This is the Delta 44. I have to verify the calibration of the S-meter graph, and it has drifted by half a dB. I don't know where that drift is. I have to check with the UADC4 here, and I click on the carrier and it has not changed. So there is an amplitude instability of the Delta 44, and it is much smaller in the UADC. I think I will live with this error because I don't know when it happened. It was 0 when I started this measurement over 30 hours ago, and whether the average has been halfway between 0 and 0.5, I don't know. But since the level is now half a dB higher, the error I make will be somewhere between 0 and half a dB in the direction that it will not look as good as this really is, the result I find here. And I have saved this and will look at it with the pixel editor. Evaluating the UADC4 screens is straightforward, and it has given me these tables of pixel information, and I will feed them into Excel. This is the result, and the data points I get are the triangles, and I can see, as compared to previous measurements when using this as an amplifier, I get a slightly steeper slope. 10 points here tend to be above the line I had before, while points down here are below. So it's steeping a little bit more. This is based on the UADC4 points. The Delta 44 data from the same period of time is more difficult to evaluate because I want to come closer in frequency separation. So I have to start by getting the center of gravity of this curve, and I have to do that in the linear power scale. So I have to convert from logarithm to power, then compute the center of gravity to get the pixel where is frequency 0. So here I have coordinates, and then converted from the y pixel to decibels, and then to power in linear scale. The product of power and x coordinate comes here, and then I take the sum of those, divide by the sum of those, and here's the center of gravity, point pixel number 555. So the center of gravity, 555, is here. Not at the center of the peak, but close to the peak itself. So intuitively finding the center of a logarithmic peak like this is not advisable. Do the computation. The data points from the Delta 44 come here, a little bit above the line I have drawn before. So they agree completely with the picture from the UADC4. I have plotted the data points on this graph where I had previously a curve for the Wenzel oscillator I measured long ago. And it's the same but more clear. It's better at higher offsets, above 100 Hertz or so. and it's a bit worse at close separations, about 2 decibels, 2.5 maybe here. Red points are from the delta 44 and blue points are from the UADC4, and they agree completely well. Here is the response from the input to that feedback output. The gain is 2.3 dB, so it will oscillate, and I press bandwidth and I get the Q is 120,000, and the markers now come on the peak of the transmission, and the impedance is very close to 50 ohms, 49.47 and 3 ohms reactive. And I can change the format and look for the phase, and then we see at the peak here the phase is very close to 0. I thought I would see the phase. Well, marker and 2, it's 0 degrees, it says. So this looks good, and this is what I have been using in the first test that I have just shown, and then I was using the box like this. The feedback circuitry is here with the diode and the resistor. Very unstable and primitive arrangement, because I will change this for other amplitudes to see how that affects performance. I have added a screen now. It might make stability a little bit better, because air circulation will not affect it as much as before. I saw that when running it as an amplifier, that it was more stable when I had something preventing air circulation. There could also have been some RF pickup by this unit, although I don't think so. The screen has caused a frequency shift of something like, could it be 2 Hertz or so? And I will have to clear the spectrum, the correlation spectrum, and then wait quite some time, because it will now get a new temperature, a little bit warmer than before. Here is the delta 44 screen, saved after 2.5 hours. Drift has been small, and statistics is good enough to evaluate up to plus minus 15 Hertz or so. The close range points I get with the screen fit with the old ones, except here where there is a small error when the offset is as large as 16 Hertz, probably because the statistics wasn't good enough. It was just 2.5 hours. I have shorted one of the diodes like this. That reduces the power by about 4 decibels, and that will perhaps affect the sideband noise somehow. The frequency has changed by about 1 Hertz. I have a feeling it is caused by something changing in the crystals. I wouldn't have seen it when using this unit as an amplifier. It would just be a small phase jump that would not affect the frequency. The level I see here is properly set, it's 0. I had to decrease the attenuation after this selective amplifier, or rather oscillator, to make this collection of data happen at the same signal level into my analyzing circuitry, the dual channel direct conversion receiver. So I save this at 4 dB lower power. Noise is about 4 dB higher at close range, and of course also at wide range. So it seems I should instead increase the power. I have disconnected the resistor here from ground, and now the oscillator runs with compression in the amplifiers, and the power level is about 2 dB higher than it was originally. Now with a higher power on the crystals, not much but a little higher, I see bursts of crystal noise now and then. Here is one, for example. You can see on both sides, and it stretches out here as well as here. And it was significantly worse just when I started it, but then the frequency stability was very poor because it was warming up. This is the UADZ4 at 44.1 kilohertz, and I'm centered on the carrier and checking the calibration, and it shows 0 as it should. So far good. Then I select a point here where the noise floor is flat, let's say here, and then a limited frequency range, and that is in order to avoid the spur that is here. And I wait for the noise floor. The noise floor is here, minus 153.7 dBc per hertz, and with a correlation advantage of 7.5 dB. That is here 161.2 at 265 hertz. This is about 10 decibels above the line I had when the output amplitude was limited by the diodes and the resistor. So allowing amplifier gain compression to set the level of oscillations in this kind of oscillator is a bad idea. And I don't need to evaluate more points from that image, because I can see that the values are really bad. I just checked the delta 44 also. There has been some frequency drift, but not that bad. I checked the level of the carrier, and it's properly calibrated, showing 0 here. And then I go for a frequency 10, 20 hertz up approximately. I don't care to make it very accurate, because to compensate for the frequency drift, a 1 hertz up or down isn't important here. So at this point, the correlation advantage is 8.6, and the theoretical limit is 18.6, so statistics is very good, as one can see from the smooth green curve here. The level here, I have to wait for a while. Well, 129.7 plus 8.6. That is here, minus 138.3 at 20 hertz. So the degradation I have running this way without diodes to limit the amplitude is bad by about 10 dB, also at close range. Well, this is also fairly close range.